So I already making the session there.
Okay. Good morning, everybody.
Sir, just a minute, sir.
Sure.
It will take 1 minute time.
Okay. All right.
Yes. Yes, sir. It is live now, sir. Sir, I welcome Dr. First of all, I welcome you all for the technical session 2 of UASG 2021. I like to introduce chair and co-chair of our session. Chair is Dr. R.D. Garg, sir. He is the professor in the Department of Civil Engineering in IIT Roorkee, and the session will be co-chaired by Dr. Saurabh Vijay. He is the assistant professor in the Department of Civil Engineering in IIT Roorkee. Sir, in this session, total we have 10 participants. Out of 10, 2 are international presenters and 8 are national presenters. And I also like to give some guidelines, same what we discussed, that totally 10 minutes for each presenter, 7 minutes for a presentation and 3 minutes for question and answer session. And I'll also like to give one announcement that the best quality papers which are selected in this conference will be published in the PFG journal, and the others will go to Springer. And also the extended version of the papers will be collected if they wish, and it will be published in the Journal of Unmanned Vehicle System. Thank you for following me, sir. I request now Adi sir and Saurabh Vijay sir to take over the session.
Okay, thank you, Pratibha. Thanks for just comparing the session. I welcome all of you. All the participants who have actively participated in this second conference on UASG, that is Unmanned Aerial Systems in Geomatics. Yesterday, you all must have participated in the inaugural session, and the speakers have highlighted the importance of UAS for various type of works. This conference is basically focusing on geomatics, but we all know that UAS has got so many applications in almost each and everything. So with this, I again welcome you, as well as thank you for participating in the conference. I will like to start the technical session 2. So in this session, we have got 11 papers, but so far 6 persons have joined, and one person has told his ability to give the presentation. So we will run the video. So basically, as Ms. Pratibha has told, we will like to give 7 minutes for the presentation and 3 minutes for question answer. Still, since we have got a few more minutes left, if any topic is very interesting and the audience want to ask more question, I think 1 or 2 minutes question answer session can be extended as such. All right. So I also thank my co-chair, Professor Saurabh Vijay, for helping me out in all these things. And as you all have been told that your presentations as well as paper will be evaluated for the best paper as well as for publication in the journal. All right. So I think now it is time to invite the first presenter. Mr. Chandrahas Singh, are you there? Mr. Chandrahas Singh?
Hello.
Yeah.
Hello. Good morning, sir.
Good morning. Good morning. Okay. Good that you are here. So Mr. Chandrahas Singh is presenting his work on review of unmanned aerial vehicle swarm system, coordination and communication. All right. Good. So over to Mr. Chandrahas, please.
Thank you very much, sir. Good morning, Chairman, sir, and Co-Chairman, sir. Today, I am going to present my paper on the topic of review of unmanned aerial vehicle swarm system, coordination and communication. These are my contents. First off, I would like to introduce what is UAV, UAV swarm. Then we will go to the UAV communication architecture, and then finally conclusion and challenges what we are facing in the field of UAV swarm system. So UAV, as we know that the UAV stands for unmanned aerial vehicle. Is the three main components of the UAVs are the aerial platform, the ground control station, and communication radio. The flight of UAV may operate with various degrees of autonomy, either under remote control by human operator or it can be controlled by autopilot. Now, the UAV, what is UAV swarm? Swarm techniques are inspired by insect hormones A UAV swarm is a cyber physical system. The most important aspect of the autonomous system is the decision chain that occurs in a lieu of human operation. Now, the movement and task completion of UAV operated is completed, controlled by humans making decision and controlling the operations of the UAV. So finally, we can say that the swarm or fleet of swarm is a system, or we can say that fleet of unmanned aerial vehicle is a set of UAV that works together to achieve a specific goal. Now, come to the what are the advantages of the UAV swarm system? In terms of stability, the multi-UAV system, single UAV out of control are nothing serious as other UAV will continue to operate and carry out their mission successfully. In terms of extensivity, multi-UAV system can easily increase the range of operations and increase the visibility of missions multi-dimensional. Now, using the multiple drones simultaneously or parallel, then we can increase the mission. The autopilot, onboard autopilot ensures controls flight according to flight plans and other instructions received from the centralized ground control. In UAV swarm, all can keep UAVs completely self-sufficient. If we talk about the cost, UAV swarm missions can be completed at lower cost. It would have cost more to raise resources at once, but the benefits in terms of price are many times. If we talk about the communication range mastery in the UAV swarm system, one UAV that is known as a master UAV that communicates with and controls the ground and sends messages to other UAVs that extend the range of our communication and great can complete the mission at a distance. And the radar signature of the UAV swarm system is very small. So the security it also enhances. And the field coverage we can, as we have mentioned that by using the multiple master system, then we can increase the field coverage. Now, we talk about the UAV swarm communication implementation. The communication architecture plays an important role in intelligent control and autonomous collaboration of UAV swarm system. In the primary stage of the development of UAV swarm, a central station was available and powerful enough to communicate with the other members of the UAV. Therefore, the centralized approach was extended from the traditional single UAV system to UAV swarm communication architecture. As the swarm system grows in size, the centralized approach is proposed. The centralized approach has a more complex structure and organization, but it does reduce the swarm's dependence on control, ground control station. So we can UAV swarm communication divided in two parts: the semi-autonomous mode and the fully autonomous. In the semi-autonomous mode, UAV communicate with the designated control station. And in the fully autonomous mode, this UAV swarm is interconnected connected communication that allows information to be shared within the UAV. Now, this UAV swarm architecture, then we can use the UAV swarm architecture can be classified in two types. The one is the centralized ground control communication architecture, and second one is the decentralized UAV swarm communication architecture. In the figure, we can see that in the circle, this is the decentralized communication architecture, and this one is a centralized communication architecture. Now, in the centralized communication architecture evolved from single UAV system and was implemented for UAV swarm technology. As shown in figure, there is a central master node. This is the central master node which communicate with all other UAV connected. Each UAV forms a one-to-one relationship with the ground control station and directly receives control command from the central command center. This type of centralized communication architecture is relatively stable and adopts simpler routing algorithms and has a smaller. When the size of UAV swarm and the coverage area of the mission are small, this type of communication architecture generally we use. The real-time application of this is this type of swarm communication architecture is like a surveillance in a Kumbh Mela. Now, if we talk about the decentralized UAV swarm communication architecture, because of UAV operated high missions may cover large area. UAV frequently connected and disconnected to the network. As a result, UAV swarm and ad hoc networks are considered the best choice in this. Under decentralized communication architecture, UAVs connect real-time interactive communication in ad hoc manner, and thereby eliminating dependencies on the ground control station, eliminating the communication-based restriction. further, the decentralized swarm communication architecture can be divided into three parts: the single group swarm radio network, multiple group swarm radio mesh network, and multi-layer or hybrid swarm radio mesh network. In a single group swarm radio network, an interval communication of the swarm does not depend upon the ground control. The communication between the swarm and the ground control station is a single point link relying on a specific UAV known as a master UAV. In this system, the other UAVs are relay nodes that forward data within the swarm. Using this method, UAV in the swarm can share situation information in real time to optimize collaborative control and improve the efficiency of this UAV swarm system. The mutual communication between the master UAV and control stations also enables the upload and download of swarm information, including instructional information. So the the two additional types of transmitters are necessary in this case: one for communicating with other UAV at low power and short distance, and one for and other for the communication with ground control station to the master UAV at high power and long range. In the multiple group swarm communication mesh network was used to address the shortcomings of the single group swarm communication radio mesh network. Multi-group swarm radio mesh network integrates both centralized approach and decentralized approach. The different types of groups have different applications depending on the mission. Overall, the architecture is organized in a centralized, while the difference is that the intra-group UAV communication with each other is done in a ad hoc manner. The intra-group communication architecture are the same as the intra-swarm communication architecture, as we can see in the figure number 11, that the intra-group, the group-to-group communication are performed through the control station. Here we can see that. So the master UAV are still responsible for communicating with the control station, and when mission scenario is required, a variety of UAVs and multiple group swarm radio communication mesh architecture is employed. Now the last one is the multi-layer or a hybrid swarm radio mesh network. This type of network is suitable for mass variety of UAVs. As shown in figure, this architecture is significantly advanced compared to the multi-group swarm radio mesh network. Architecture, a group of adjacent UAV of the same type constitute an ad hoc network, which is the first layer of the communication architecture. All UAVs are interconnected with each other through this node. Now the communication between any two UAVs in the hybrid architecture does not require ground control station. Mutual communication of UAVs in the same group takes place at the first level. The communication between UAVs in different group is routed through the master UAV. We can see that these are master UAV. So no single point of failure in the multi-layer swarm radio method, and this type of architecture is robust. Now to the discussion. We know that the UAV swarm communication architecture technology has already made a great. When faced with different mission scenarios, there are different communication architecture to choose from. Centralized communication architecture is suitable for scenarios where the UAV small task is relatively simple. Each individual UAV requires a long-range communication link with the ground control station. This decentralized communication architecture expands communication coverage through a multi-hop network. This dedicated master UAV is responsible for UAV to control station communication. The single group swarm communication architecture is appropriate for a swarm of the same type of UAV, while the multiple group swarm mesh network and multi-layer swarm mesh network architecture can be deployed using different types of UAVs. And in a multi-group swarm radio mesh network, the communication between two adjacent groups can also suffer from delays. In addition, in terms of robustness, the multi-layer swarm radio mesh network architecture is relatively reliable because it overcomes single point of failure. Now, coming to the conclusion, this paper provides a concept-level proposal, preliminary developmental literature review for use of wireless radio network as a communication central control station for UAV swarm. It provides an overview of UAV swarm industry development efforts for UAV swarm and in-house applications. UAV swarm and this paper reviews the developmentally tested paperwork and provides direction for future work about the UAV swarm. The specific development and coordination capabilities of autonomous swings with UAV to UAV communication are central to advance the utility of UAV swarm. Although this swarm technology is not yet practically used in commercial application, but it holds considerable potential. Now, talking about the challenges. UAV swarms are highly mobile and their topology changes frequently, so requiring a communication network with low latency and high reliability. Therefore, it is necessary to design communication architecture and routing protocols with good applicability. The swarm communication may be intermittently associated with the rapidly increasing feature of UAVs and frequent change in mesh networks. This has always been one of the important problems with routing protocols. Therefore, the solution to the problem of intermittent contact will remain the focus of research in future. Now, currently the most of the proposed routing protocols focus on performance improvement. However, security is an important material that cannot be ignored in any communication network. Necessary to propose new mesh network solutions, including security components. So, security is very essential right now in the UAV swarm. And one more important challenge is energy. Energy scarcity plays an important role in UAV networks. With the energy crisis, concern about power savings UAV mesh network, line radio network, and wireless sensor network. The applicability of these protocols in various UAV swarm radio network scenarios has been tested. So these are.
Yeah.
Okay, thank you, Mr. Chandrahas. It is a good topic, and it is true that there are so many challenges in the work. Now I request Professor Saurav Vijay, co-chair of the session, to kindly conduct the question answer session.
Yeah, I mean, we don't have any time left, but I have one short question for you. Do you also, can you please highlight the applications of these three networks you proposed? Like you proposed 3 networks, like do you also think of any application areas?
Sir, in terms of the centralized swarm communication network, right now we are using the UAV swarm system in the cloud surveillance, like in Kumbh Mela in Haridwar, right now we are using this kind of UAV swarm system.
No, application in terms of, I'm asking, in agriculture areas, in urban.
Yes, in right now we are not using in the aerial mapping or in the agriculture area. Sir, right now I am working on it to use in the aerial mapping, because it can reduce the timing and the cost of the surveying. So right now I'm working on it.
Okay, so we have not received any question from the audience. So if Dr. Adigar sir, do you have a question?
It's okay. I think we can ask the audience. Few audience are also connected live. So I think if they have any question, then we can ask. Otherwise, we switch over to next speaker.
No, we have not received any question yet. Maybe
okay, all right.
And they will reach out to you. Okay.
I think it is all right. So yeah. Now we go for the next speaker. So next speaker is Mr. Rohit Lal. Mr. Rohit Lal, are you present?
Yes, sir, I am present.
Okay, good. Welcome to this conference. So Mr. Rohit Lal will present his work on deep SCT based person following drone. Okay, I think it seems to be an interesting topic. So over to Mr. Rohit Lal.
Yes, sure. I'll just share my screen. So can you see my screen?
Yeah, we all can see.
Yeah. So good morning, everyone. My name is Rohit Lal, and I am currently a final year BTech student at Adversarial National Institute of Technology, Nagpur. So today I am here to present my paper on deep SCT based person following drone. So let's see the contents of it. So basically, we will first tell you about the problem statement, application, and what all paper contribution we have made. We also have done rigorous comparison with previous work, and we will also show some qualitative and quantitative results along with videos, and end it with conclusion and future work. So let's move on to the problem statement. So as I mentioned in the paper name, we are trying to solve the problem of autonomous object following from a drone feed. So basically, we are trying to develop a system that does not require human assistance. And we will be using a deep learning and computer vision technique for tracking the target object. So now the system we develop should be scalable and have application and vertical domains. So the person following drone has various applications. So one can be in defense and surveillance. So this can be used as an intruder detection. If an intruder comes into an area, so we can track it and locate where the person is, where the intruder is. And the second application can be in movie making, where we can use this person following drones, and it can also be used as an autonomous load carrier for elderly people. So these are three main important applications of our project. And next, moving on, we will be showing some of our paper contribution. So basically, we have implemented our mechanism, which was named Deep SCT, and have rigorously compared it with our previous method. So we developed an environment in Unreal Engine as well, with the help of ASM environment. So the main aim was to solve the problem of long-term tracking. So we need to keep on tracking a person or any object for a long term. And we have done that, and we have compared its performance for both long-term and short-term. Yeah. So there has been already a lot of work done in the tracking area. So basically, we divide this work into three parts. So the first part is classical computer vision based tracker. So for classical computer based tracker, we see that it had very real time application, and it can be very fast in computation. And the next benefit it had was it can preserve the identity of the object. But it had major drawbacks, like it produced a lot amount of false positives and false negative. Also, it was not able to handle the occlusion as well as drastic changing lighting condition. So this rules out the possibility of using only classical CV based tracking. So next, we see that there has been recent development in deep learning based tracking methods. So we can basically use two types of deep learning based tracking method. One can be based on detection, and other can be based on re-identification. So in detection, we basically use an object detector algorithm and keep on finding the person, and have IOU score calculated, and we can track in this way. But the issue was that it didn't have any identity preservation method, and it was very computationally costly. But on the other hand, its advantages were that there were very less false positives and false negative, and also like it was able to tolerate more variable writing condition. Next, we had re-identification based tracking. So basically, this was robust against occlusion and was viewpoint invariant as well. It can also handle like very fast moving objects, because in drone we have sometimes rapid movement, and mostly classical vision based techniques fail in this regard. So we see that there are some drawback of this method also, and it was that we saw that it was computationally very costly to compare each and every person for re-identification. And it was not basically a tracking. It can't be used as tracking because it doesn't use some information from previous frame. So we are just basically using one image at a time for tracking. So these were, we can see that we had three methods, but none of them had like completely solved the problem of long-term tracking. They can track for short-term, but for long-term, they have problem of error accumulation and various other problem like occlusion and computation speed. So we basically need to optimize all this and make an algorithm that can work really well in long-term tracking situation. So here we present our method, which is named Deep Self-Correcting Tracker. In short, we call it Deep SCT. So what it does is basically uses all these three methods in conjunction. So we saw that the problem of one was the advantage of other. So why not to use the advantage part of all these algorithms and combine it into one algorithm, such that it is really fast and also provides a very high level of accuracy. So what we did was we first taken an image from the drone, and then we basically feed it into a backbone tracking algorithm. So for backbone tracking algorithm, use CSRT, which is very fast, which is computationally and inexpensive. But it was also, as we saw earlier, that it also produced a lot of false positive. So in most of the time, this backbone tracking algorithm would run, and there is a correction mechanism which was used using detection subblock and re-identification subblock. So what it did was we used this re-identification and detection to correct our position after a certain interval. So if suppose we have an error accumulated after like 100 frames or 200 frames, so after 200 frames we will run this and we will correct all the position of the tracker. And basically this provided a significant boost in tracking performance, because earlier what used to happen was that once the tracker gets lost and it was not able to come back to the original person. So what these trackers do, they basically correct the position. Suppose if a person goes out of the frame, or if a person is occluded by another person or any other object. So what it will do is it will keep on checking for the person using this re-identification subblock, and it will keep on checking for the person and correct it once the person is visible again. So this was like a major drawback in backbone tracking algorithms. So so these were some major drawbacks in backbone tracking algorithm, which is being corrected by the identification and detection subblock. So in this way, we significantly improve the performance of CSRT or any other backbone tracking algorithm. So for testing, we developed our own simulation environment, as you can see. So it is based on Unreal Engine and ASM. So the ASM is like an open source software. So we use that. And we can see that it's very closely matched to an urban environment with several instances of occlusion. And we also added rapid camera motions and environment disturbances. You can see in this video. I will later show you a video also. Yeah. So now coming to the quantitative results. So for tracking, we have very famous metrics called success and precision plot. You can see that we have compared our deep SCT with various other backbone tracking algorithm. Some of them are CSRT, KCF, median flow, and MIL. So these are correlation based and some various old tracking algorithms. So what we see that our deep SCT algorithm is consistently higher than any other backbone tracker. So because this is the reason for this is because we are able to track for a long horizon time. Other trackers generally fail after some time, but our algorithm doesn't fail. It keeps a very high area under the curve, and hence we were able to conclude that using a baseline tracker along with deep SCT correcting mechanism is almost always better, because it was able to rectify the tracker position at it was able to rectify the tracker position after several instances. So we can see that there is a significant improvement in both success as well as in precision. So yeah, moving on. These are the qualitative results. Okay, I think. So I'll just show you the video, like what I meant. So is the video visible? Hello? Yeah. So as you can see that the green is the ground truth. So green is our tracking. This is the CSRT tracking, which is only the baseline, and this is the ground truth. So as you can see, wait, I'll just replay the video. Initially, it was tracking well, but after some time, you can see that it has shifted to other, and now it is not able to correct itself. You can see that now it has completely gone. Now coming back to our SCT method. Is the video visible? Hello?
Yes, it is.
Mr. Rohit, it's
yeah,
visible.
okay.
Yeah.
Okay. Thank you for the confirmation. Yeah. So next I will show you that what deep SCT plus CSRT does. As you can see that the green box is our deep SCT plus deep SCT corrector, and you can see that earlier at this point of time it had already lost because of these kind of objects, and you can see that there is some lamppost is there, and there are various other person which will cross. So it is now not losing it. You can see it's consistently tracking. Even after there are so many occlusion, even after there are trees have occluded, a person riding a bike has occluded. So there are various cases of occlusion. It is still not losing this track. So this shows that our algorithm is really better. And you can see that you can see that it first went to other person, but after a few frames, it again came back to the original person. So this shows that how powerful our algorithm is. Yeah. So next we will show you that we have implemented. Yeah?
Mr. Rohit, please finish your presentation. We're exceeding the time.
Okay, sure.
Please conclude.
Sure. And this was like we did it on the simulation environment where we control the drone. And next, just wanted to say that we have basically made this. We have basically proven that our method was a little better than the classical based method, which were prone to error accumulation. We have also open sourced our code for person following environment as well as the detection, so anyone is able to use this. So yeah, so we haven't written the controls for drone and obstacle avoidance for the environment, so we will be working on that as well. So thank you for that.
Thanks, Mr. Rohit. I have two questions from the audience. So first question, is about is the drone following be done in indoors or in deep forest environments?
So basically, we are trying to do this in the outside environment. So not in indoors, but on outside environment, like for in movie making or for like in defense application outside drone. So it will be basically important. Yeah.
And the second question is, what would you like to suggest when in terms of obstacle avoidance, when the drone is flying in opposite direction of the camera exposure, for instance? Do you have something to say on this?
So basically, like in this, we were aiming to develop the tracking algorithm. So we haven't basically implemented our obstacle avoidance yet. So we will be thinking about that. So we haven't thought like how to do the obstacle avoidance, and we are basically working on it.
So I think it will be great. Yeah, it will be something you would like to do in the future when you have some of that sort happens. So we have one more question, and then we can wind up your presentation.
Yeah.
So Amit Kumar is asking, does the algorithm depend on the quality of the input in video images? So can it work well with the low quality videos too?
Yeah, so basically what we are trying to do is trying to optimize the speed of the algorithm. So suppose if we have a very huge image, then we can, even after from a very great height, we can track the person. But if the quality of image is very low, then tracking of person might not be very feasible. Suppose we have the drone at 50 meters or at that height, the person, if we have low quality image, then the person itself will not be visible and tracking won't work. So it's better to have a higher quality image. But for lower heights, if we have around like 5 meters, something like that, then it's not an issue. Like we can have, we are actually using it for 5-10 meters, then we are having image of 512 cross 512. So yeah.
Okay, thanks, Mr. Rohit. It was a really nice presentation. Professor Adigar, sir, do you have any further question, or we can move?
No. I think thanks, Mr. Rohit, for a good presentation. So now I would like to invite other speaker. So in the line we have got Mr. P.S. Singh from NESAC. So Mr. P.S. Singh, are you there?
Sir, Mr. P.S. Singh is not here.
He is not there. Okay.
Yes,
okay. All right. In that case, we will switch over to the next person. I think he is from UTM Malaysia, Mr. MHM Room. Are you present?
Yes, sir. He is
okay,
present.
Mr. Mohammed. Mr. Mohammed, welcome. That it is good that we are able to connect with you, and our participants will get more exposure regarding the work, whatever is going on in Malaysia. So Mr. Mohammed will present his work on the potential of unmanned aerial vehicle system for three-dimensional smart cadastre in Malaysia. Okay, I think the cadastre is for the large level mapping. Is it December? Okay, good. Very interesting one. I think after that, we also have the presentation on the similar topic for the cadastral mapping, etc. So over to you, Mr. Mohammed. Please present your work.
Excuse me, sir.
Yeah.
Sir, he asked to play the video.
Okay, all right, all right. So just we can have the video presentation.
Yes, sir.
From him. All right, thank you. So you please run.
Greetings to everyone present in this conference. Our paper is titled 3D Point Cloud Segmentation using a combination of ransack and clustering methods. There are three of us working together on this paper, each from two institutions, the Northeastern Space Application Center, or NISAC, from the Department of Space.
Oh, I think Mr. Mohammed is told that it is from the previous author, I think.
Okay.
Sorry, sir. Just a minute.
Sorry, I interrupt. If you have problem, I can make presentation live. Student from this technology.
I think you are always welcome to present it instead of video. There's a recording. So if you are able to present, then it will be better. All right.
I will present.
Yeah, please. Yeah, that will be good. Yes, you may please start the presentation.
Okay. Can you see my slide?
Yeah, we are able to see it.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good afternoon to everyone. My name is Muhammad Hafiz. I am from UTM, Malaysia. So I will present about my paper, and the title of my paper is The Potential of Unmanned Aerial Vehicle System for Three-Dimensional Smart Cadastre Application in Malaysia, a review. So my presentation will cover several parts like the introduction, unmanned aerial vehicle system, what is the smart cadastre, real study, the analysis, and also the conclusion. So the introduction, the use of UAV photogrammetry for acquiring geospatial data has significantly increased over the last decade. The development of artificial intelligence, AI, and robotics are the other factors that expand the usage of the UAV system in the 3D modeling application. The evolution of the computer vision algorithm and also the computation technique has improved the processing time, and mostly the process to produce a 3D model is automated. The 3D modeling has become very important in many applications because the real information can be extracted from the model. The main objective of this study to analyze the capability of UAV system used for 3D smart cadastre application in the Malaysia. And several factors will be analyzed, like the type of platform for data acquisition, the quality of the 3D city model, the type of the sensor, and also the limitation of the UAV system. What is UAV? There's many definitions of UAV. has been given by the researcher and also the organization around the world. But generally, UAV can be described as a class of aircraft that can fly without a pilot on board present in the cockpit. It also can be operated in various modes such as autonomous, semi-autonomous, manual, or combination of any this mode. And also there are many terminology has been given for describing this system like drone, UAV, remote pilot vehicle, and many more. The terms are different because it depends on the field or organization for use the technology. For example, the term of UAV widely used in geospatial and geometric field, while the term of RPV, remote pilot vehicle, is commonly used by United States Department of Defense. There are many types of sensor that integrate with UAV, like digital camera compact, the most common sensor, DSLR camera, multispectral sensor, hyperspectral LiDAR, and also the thermal. Because of this development, it made the application of UAV become expand. Today, UAV can use for many applications like search and rescue, parcel delivery, disaster management, precise agriculture, mapping, weather forecast, 3 city model, and also wildfire monitoring. So next we go to what is 3 smart cadastre. Basically, 3 smart cadastre, the main objective of 3 smart cadastre to establish multi-purpose cadastre based on spatial analysis platform. This smart cadastre required use the sensor like LiDAR airborne.
Excuse me, Mr. Mohammed.
Sorry?
Excuse me, Mr. Mohammed. Your slides are not moving. Are you moving your slides?
Yes.
Because we are able to see only the first slide. So
the first slide.
Yeah, I'm just able to see your first slide.
Okay.
Maybe you can open in the Windows.
Sorry.
PowerPoint. Because it seemed like you open in the browser. Yeah, I think it should.
You can see?
Just move it. The next slide. I think it's moving now.
Moving. Okay.
Yeah,
sorry.
Thank you, Mohammed. Yeah, no problem.
I'm very sorry. Okay, the main objective of 3 smart cadastre is to establish multi-purpose cadastre-based spatial analysis platform, and the sensor are used in this project like airborne LiDAR, mobile laser scanning, TLS, 360-degree camera, and also the matrix camera. And the data used in this project like LiDAR, orthophoto, DTM, DSM, control line, oblique image, 360 images, 2D and 3D image. And this project was implemented at the major city in Malaysia, which is Kuala Lumpur and the Putrajaya. All of this sense of this data will compile together with cadastre information and also the map and 3D based information in order to develop a 3D cadastre database for Malaysia. Next, we go to the next in Malaysia, Department of Survey and Mapping has planned to expand this project into another area in Malaysia, especially in major city. This project involved a huge amount of cost because the sensor used in this project is very advanced and expensive technology and also required very skillful operator. As we know that the changes always happen in the city due to economic growth and population increase. Therefore, the database of 3 smart cadastre are required to update in order to keep the information accepted for the portal is still relevant and up to date. Sometimes the changes only occur at a small area and a particular place. For updating data by using the original sensor or original method, I think it's not practical. So based on my previous study, as this table show the article that some of the article that I have reviewed. So we go to the analysis. As I mentioned before, there are several factors that I analyzed in order to investigate the potential of UAV system used for this application. For the first factor, type of platform, I found that the most multi-rotor platform is widely used for acquiring the per cloud of the object and features, because this type of platform is easy to handle rather than fixed swing. This platform uses using the concept of vertical takeoff or landing, and only require a small area for landing and takeoff. Therefore, it's suitable used in the place where there are many buildings. It can capture the image of a cloud very close to the building and other ground features. And the second factor is the accuracy. LiDAR and compact digital camera has been used for acquiring point cloud in various 3D application. Both sensors are capable to produce a good and accurate 3D building model in centimeter level accuracy. However, based on my literature view, I found that UAV-based LiDAR can give better accuracy than normal digital camera sensor. That type of sensor. Many types of sensors were fused with UAV systems such as mobilizer scanning and TLS. The integration with other sensors caused the accuracy of the model increase and improve the level of detail. The higher density of per cloud can be obtained too. And then the limitation of UAV system. Most of the studies show UAV suitable use for modeling in a single unit building. However, it's not suitable use in the compact area due to the pilot have difficulty to control the UAV in the small space because of the location of the building is quite closer to each other. Therefore, some of the component of the building like the wall will not cover. Fusion with other sensors such as MLS and TLS will help to obtain the complex point cloud of the building in the compact area. So as a conclusion, I found that UAV system have potential used for this smart cadastre in Malaysia, especially for updating the database. Other than that, I found that the most suitable platform is multi-rotor, and the quality of the model produced for UAV system is accurate within centimeter level. Other than that, it is most suitable or appropriate to integrate more than one sensor in order to get the high density of per cloud, because it will influence the quality of the 3D model. And in this case study, I found that the best sensor is integrate between LiDAR, UAV base, and also MLS. Other than that, UAV is capable to produce the final product in the less time compared to conventional technology. It also low cost just by data acquisition that can be employed. So that's all for me. Thank you.
Yeah, thanks, Mr. Mohammed. It was very nice and insightful presentation. Thank you very much. Meanwhile, we get questions from the audience. I have like 2 short questions. We often say that these are unmanned aerial vehicles, but we need a lot of human resources to handle this. Do you have any thoughts in this regard?
Pardon? Can you repeat the question, please?
Yes, of course. So as we say that these are unmanned aerial vehicles, but we need a lot of trained human resources in the field. So do you have any thoughts in this regard? Still, we say this is unmanned aerial vehicles, right? What do you think?
I think, yeah, we still need a human to operate the system. For example, in 3D, if we do for mapping, we still need a human, for example, to do the GCP for evaluate the quality of the map. So I think we cannot ignore the human resource.
Okay, so like okay, it's okay. I mean, the second question is regarding, because we have high-rise buildings in, like, you know, big cities. If what are the challenges do you think that when you fly a drone in between these high-rise buildings, because you don't have good GPS signals, for instance. So do you have any ideas on this regard?
Maybe we can use the other sensor, maybe like TLS, because I found one of the article, they model building at the compare area, and then they put the TLS on the building, So maybe some of the they use mobile laser scanning. Mobile scanning only cover not the whole building, but in order to get the complex 3D model, so they integrate UAV for the top TLS they put on the building, and also the MLS for cover the bottom of the building. That's my opinion.
All right. So we have not received any question from the audience. If yeah, Professor Adigag, do you have a question?
Okay, I think it is a good work by Mr. Muhammad. So I thank you for your presentation. And in fact, it is always good to see your presentation live. So, okay, thanks. Now, Ms. Pratibha, I just want to ask that I think Mr. Singh from this NESEC has sent his recorded
Yes, sir.
presentation. So, shall we show that?
Yes, sir. We can show. Like now you want to show or the last end after all the physical
Okay, okay, all right. Your suggestion is well taken. Let us first listen to those who are present here, and afterwards we can have the recorded presentations. Okay, so next presenter is Dr. Ganesh Khadanga.
Yes, sir.
Okay, are you here?
Yes,
okay,
sir.
Good. I am sorry with the other audience that since I know him personally very recently, he has been awarded the PhD degree. If any other person who is a doctorate and I am not able to address him with doctor, so please excuse me. So now Dr. Ganesh Khadanga will present his work on UAV to cadastral parcel boundary translation and synthetic UAV image generation using conditional generative adversarial network. All right, over to Dr. Khadanga, please.
Good afternoon to all. Hope I am audible.
Yes, you are audible. You please start presentation.
Respected Chairman, UASG 2021, faculty members of IIT Roorkee of Civil Engineering Department. My topic is UAV to cadastral parcel boundary translation and synthetic UAV image generation using conditional generative adversarial network. My outline of the presentation is motivation, background information, proposed method, results, future work, and references. As you know, India has about 6.4 lakh villages. The cadastral maps were prepared in 1:4,000 scale or 1:8,000 scale during 19th and 20th century. The National Land Records Modernization Program emphasized to modernize the management of the land records. Now it is renamed as Digital India Land Records Modernization Program. The basic need of this program is the updation of the old cadastral maps using modern surveying techniques like electronic total station, global positioning system, aerial photography, and high-resolution satellite imagery. The UAVs has emerged as an alternative to capture the high-resolution images. The easy maneuverability, flying below the clouds, low cost and high spatial resolution are the key attracting features of UAV's popularity. The fast image acquisition also needs faster automated information extraction methodology for the technology to meet the societal needs. Deep learning techniques has emerged as an alternative to traditional image processing techniques. The convolution neural network, CNN, has better results in image recognition. It makes trouble in terms of generating models. But as you can see, we cannot simply use the equivalent distance because of it is only calculates the global average distance. They need to inform the CNN what to train and what to learn. although the learning process is automatic, still there is a lot of manual operation to design the loss. Overall, CNN learns to minimize the loss function and objective scores to a quality result. The related works, the authors like Aishola et al. Has developed the pix-to-pix model and generated the generative adversarial network conditioned on the source image and imposed L1 loss and generated with the original image and the ground truth maps. The quality of the generated image improved as the generator and discriminator compete to each other to reach the Nash equilibrium expressed by the min-max loss training procedures. The architect of the generator is basically a unit. It consists of an encoder and decoder architecture with skip connection between them. The discriminator is basically a patch GAN. Patch GAN is basically classify each patch of n by n size whether it is real or fake. In GAN, the generator is the main part and the discriminator is the adaptive loss part. The author like Tero et al. Has also indicated the generator and discriminators are grown progressively with low resolution and then add a layer with increasing size details so that the receptive fields gradually increases. This has enabled the GAN to produce high quality output. The sliced Wassertian distance indicates that the distribution of the patches is similar and also proposed as a matrix for evaluation of the matrices. The detailed analysis of qualitative and quantitative measures are given by Borgi et al. The authors like Valesina and Rusdo used the pix-to-pix network of water feature maps and generated the river deltas and of the coastal areas. The Lucas Fetty et al. Has trained the CGAN with 4 different generators like a ResNet, DenseNet, UNet, and Embedded Net. An ensemble model was created from the 4 outputs. The author has also indicated that CGAN architecture can be considered useful model as it only needs a small sample size to generate and discriminate the cross trainings. The authors like Jihang and Zhongu et al. Proposed addition of partial dense corrections in CGAN generator for segmentation. The author Abdullah and Pradhan proposed a SegNet model with bidirectional convolution LSTM in CGAN generator and generate the segmentation map from the existing building dataset. Jafris et al. Proposed CGAN with mean square error loss for finding the faults and fractures in with limited inputs. Tauji et al. Has proposed and able to transfer the domain distribution of input images to the target image by progressively translating the images from coarser fine to coarser. The progressive translation enabled the model to extract the underlying relationship between images by continuously varying the receptive fields of different scales. The image-to-image translation is also useful in applications such as colorization, super resolution, adds to image dictation, style transfer, data augmentation, and image inputting. Coming to our class, our prime contribution in this study is the preparation of the specialized data set, training the model of CGAN, cadastral boundary extraction, and synthetic UAV image generation. The data is prepared from the UAV images and the corresponding manually digitized cadastral map files using the Python modules. The fitted module can be used to predict the parcel boundaries and synthetic images for a new data set. The work can also be treated as a practical field application of computer vision for automation of cadastral boundary extraction. You can see this is the UAV image and the corresponding cadastral parcel map. This is another data set, a UAV image and the digitized parcel map. Another one. So from these existing UAV images and the digitized cadastral parcels, we have generated a set of images of 256 by 256 size. And also we have given different color codes to the features like parcel, road, water, river, and building. And this few set of image pairs are shown here. Out of the data set was split to 500 to train and 95 as the test data set. You can see the latent random vector goes through the filter and the image. This is the generator part of the GAN. The discriminator part of the image is passed and filtered and it says yes or no. The same thing is also explained with the 2 networks. The generator network is shown, discriminator network shown, and the real samples are given. Coming to the details of the network, the generator consists of input and output. It is basically an encoder and decoder architecture with skip connections. The discriminator is basically an encoder part, and the final output is basically 30 by 30 size. Coming to the generator and discriminator perspective, with the discriminator perspective and generator perspective. This, since both the two networks are trained simultaneously, if one gets benefit, the other gets degraded. So this is what is demonstrated here. The GAN structure, the GAN takes identify using the generator model to generate the fake samples, and the discriminator model tries to decide if the image is received is fake or real. In conditional GAN, the GAN is extension of the GAN to a conditional setting attempts to guide the data generation process in a better way by providing certain contextual information about the data. The smaller patch GAN, fewer the parameters, so model will run faster. In conditional GAN, not only learns the mapping from the input to output image, but also learns a loss function to this mapping. Apply the same generic approach to the problem that traditionally would require different loss formulations. The network is again shown here. You can see image input is basically given to the dot, both the inputs. Here you can see this image was inputted, and this is also taken as an input to the generator network model. After the model was executed for 100 epochs, and Google Colab platform is used for GPU processing. And this is the result during the training stage. You can see the top one is the UAV data, the middle one is the ground truth data, and last row is the predicted data. This is done in the training stage. Now this is the data during the actual predicted boundary with the model. So this is the UAV data, this is the ground truth, and this is the, you can see all the boundaries are also, and the road also predicted correctly. Only there are little bit noises that can be eliminated by post-processing techniques. On the right side, you can see the error plot versus the iterations. Towards the end, you can see the losses gets stabilized. Now we have reversed the input. That means we gave the boundary and generated the UAV data. So this is the input on the left column. Middle column is the UAV data, and the predicted data is the last column. You can see we have given the input cadastral map, and it has predicted you can see the texture between these two images are quite satisfactory, and it is very indistinguishable. And you can also see the loss gets stabilized. The D-real, DFAC, and D-general loss all get stabilized towards the end of the training. The discussion, the predicted boundary of the UV images are shown. The error plots are also shown. The boundaries of the cadastral parcels are extracted to a great extent. However, the boundaries of many fields are partially extracted. The same can be completed with manual or post-processing activities. The textures of the synthetic images are visually very promising, and it can be used as an alternative to real UV images. The boundaries of the plots are quite satisfactory externally. Though the result is quite satisfactory, there is scope for enhancements of the result. The further experiments can be done with a larger data set, and techniques like data augmentation can be taken up to enhance the results. The automation of the input data preparation and use of data augmentation techniques, pre-processing and post-processing also are the key challenges. The use of temporal data is also a promising field. The investigations are done for the extraction of the parcel boundary from the UAV images, CDAC modules. The synthetic images are also generated using above the network, reversing the input. The proposed approach contributes to the research area of automatic generation of the parcel boundaries from the specialized data set as prepared from the UAV images. The extraction of the cadastral parcel boundaries using the proposed approach is quite satisfactory. This will enhance the ways continuously update the cadastral boundaries by revenue field functionaries. The synthetic UAV image generation approach can be used in difficult areas where the UAV cannot be deployed because of technical and administrative issues. In future, there are still constraints. The approaches like obstruction to visible boundaries because of trees and shadow. The modules are required for data augmentation, enhancement, extraction process. Presently, the methodology will help the operators in automation of the parcel boundary transfer. These are my references, and thank you. So this is what I want to talk about.
Yeah, Dr. Ganesh, thank you very much for very important work and very impressive. We have a question from the audience for you. how did you resolve the issue of burns in the agricultural lands? Because burns have some thickness. So how did you digitize them?
Okay.
Very straightforward question.
You can see from the existing data set, the burns are actually, we have taken two pairs of data. One is the actual UAV image and another is the corresponding manually digitized shape file, which is converted to an image. So I have two set of image pairs. So one is UAV and another is the boundaries. From these boundaries, I have made a pair of images as indicated in the pix-to-pix algorithm. So I have a 256 by 256 size UAV image and 256 by 256 cadastral parcel boundary. So now, since it is manually digitization, so the bonds are automatically taken care in the process.
Okay. So I have a short question. We often say the machine learning algorithms are like black box. So, and the parameters we don't have a great control on. So what do you suggest, like what should be done in the future in this context?
You see, that's why in order to have a better performance in the machine learning process, the generative adversarial network or conditional generative adversarial network has come up, where you can give additional input to the image in the form of, you can see here. You can see these additional images were given here, input as an input. So this basically helps in improving the, you can see these two pairs of image, and here is the additional input we have also given to the generator. So this additional input may be either full image or some boundary information or some texture information. So with this additional image inputs, we can enhance the quality of the extraction.
Okay. So we don't have any questions left. Professor Adigar, do you have a question?
Yeah, Dr. Kharanga, I have got a small question. Like apart from this technique, CGN technique, have you tried any other machine learning technique for your work?
Yes, sir. There are other techniques like this simple unit is also a segmentation process, which is basically an encoder and decoder part. And VAG16 and VAG19 are also model that was also explained in my last presentation. And that model can be treated as a deep learning model to extract the cadastral boundaries.
Okay, all right. Thank you. So we thank you for your presentation. Now we go to the next speaker. Next speaker is Miss Ankita K. Patel. Are you there? Miss Ankita K. Patel, are you there?
Yes, sir. Yes, sir.
Okay. Okay, you are welcome.
Thank you, sir.
Now, Ms. Ankita will present her work on coverage estimation using probabilistic line of sight model for unmanned aerial vehicle communication. Yeah,
okay.
Over to you.
Thank you, sir. Is my screen visible to you?
Yeah, it is visible.
Okay, good morning, one and all. So topic for my paper presentation is coverage estimation using probabilistic line of sight model for unmanned aerial vehicle communication. So as we know, there are various applications of UAV in the area of wireless networking and communication. And one of that which I have taken is search and rescue operation for disaster affected area. So if for this area, this UAV can provide a wireless coverage for the serving area. It can act as a base station or relay to provide wireless connectivity. So this will be helpful for fast recovery of the system where the infrastructure is completely lost. So this can be added advantage of UAV that it can be act as a flying base station for that. But the communication part is totally different for whenever we talk about UAV and the conventional wireless communication system. So radio propagation in this is different. So for this UAV to ground propagation, we got more line of sight part. So line of sight, the link is predominant in that. So that is the added advantage of this communication. So for that purpose, we had our study is basically for line of sight communication. So there are various factors which parameters or factors which we had taken. There are several factors are available, but we had concentrated on 4 factors only. So one of them is the environment. So we had taken basically different types of urban environments. Then 3 more factors we had targeted. One is UAV altitude, another is elevation angle and communication range. So in the diagram, you can see this HT is nothing but the altitude of UAV. Then R is the ground distance between receiver and UAV, and theta is the elevation angle. So these 3 parameters basically we are targeting for various environments. So what is the purpose of our study? So the main purpose of our study is to develop a generalized elevation dependent line of sight probabilistic model for air to ground communication and estimate area coverage for disaster affected area. So our study is divided in 2 parts. First part, we had taken the line of sight model. So we had developed a generalized line of sight model based on statistical parameter. And second part, we had estimated area coverage based on the developed model. So we have defined an algorithm for that. And this will be helpful for the RF planning of the city, which is not dependent on site specific information because it is based on statistical parameter. Now, and in literature, various studies are available for channel modeling approach. So one of them is geometry based. So in this model is based on the whatever geometry you had taken. And second is measurement based. So this is very site specific modeling. So both these methods are not generalized method, and we are targeting for generalized method. So we had taken the third one, which is the statistical parameter based. So studies are available for the higher altitude. And our target is mainly for the low altitude. We had taken altitude below 500 meters by considering the guidelines for flying altitude of UAV. So this is one part of our literature survey. Second part of literature is based on the area coverage. So there are various algorithms are available, either the relative distance between UAVs, UAV altitude or coverage radius. But our focus is to define a model which is elevation based. So we had defined a model which is elevation based and taken the area coverage for the same. So for the methodology, so to develop any RF model, we need a layout and characteristics of building for any environment. So for that, we had taken that International Telecommunication Union guidelines. They had defined statistical parameter alphas, betas, and gammas to describe a certain area. So these parameters, if I define, so alpha S is nothing but ratio of build-up area to the land area. Beta S is nothing but mean number of buildings per unit area, and gamma S is nothing but a building height distribution. This is done as per Rayleigh probability distribution. So based on that, they had given one LOS probability model. So this is based on height of transmitter, receiver, alphas, betas, and gammas parameter, but it's a complex equation. So our aim is to define a simple equation and elevation dependent model. So for that purpose, we have simulated the ITUR model for 4 different areas: suburban, urban, dense urban, and high-rise urban area. So for the simulation, we had taken area of 1 by 1 kilometer by 1 kilometer. We had design a building, a distributed building, and that altitude maximum we had taken is 500 meters, elevation angle for 90 degree, and azimuthal angle for 360 degree. And this graph is showing the simulated result. So we had applied curve fitting method to define our model. So next is our model. So this is what is our model. It's a simple model as compared to the previous equation. So it is based on elevation, which is theta defined over here, and 4 simple parameters, A1, A2, A3, and A4. These parameters we had calculated based on least square curve fitting method. And here is the table for all 4 parameters. And if we go with the result of the developed model and ITUR model, you can see that it is going line by line. So it is following line by line to the ITUR model. So this is what is the model which we have developed for line of sight communication. So this is the first part of our study. Now, in the second part of our study is the area coverage estimation. So for that, we have to do the accurate area coverage estimation, because for any application, we had taken disaster affected area. So we have to find out that how many UAVs will be required to cover particular area. So for that, first of all, we have to calculate area coverage for the single UAV. So that can be achieved by various methods. So we had taken a method based on optical line of sight. So for that, we need a building and terrain database and a building blockage probability. So what will be building blockage probability? That can be easily find out from this diagram. So it states that each building lying between UAV and receiver is below line of sight ray. So this is what we are saying, that if it is line of sight, that is mean that is under coverage area. So we are assuming that the building which is between transmitter and receiver are below line of sight. So that will give me the area coverage. So this building blockage probability is nothing but the estimate of optical line of sight between UAV and receiver, or between transmitter and receiver. So this can be based on the distance as well as 3 more parameters, which is alpha s, beta s defined prior, and a line of sight probability model which we had developed. So now the algorithm is being defined. So this algorithm is defined in the 4 steps. So the first step is calculate number of building between UAV and receiver. So for that, we had taken a ray of 1 kilometer, and that we find out how many buildings are available, or expected number of buildings we had calculated. Then second part, we had calculated the buildings between UAV and receiver. How many buildings are coming between transmitter and receiver? So that is given by BUR parameter. It is dependent on R, which is the distance between transmitter and receiver, and alpha s and beta s. Then second step is to obtain the distance of each building from a transmitter. So that will give us that how many buildings are coming under line of sight from the transmitter. So for that, first we had taken a uniform distribution of the building. Then we had taken distance between each building, and then we defined the distance of each building from the transmitter. So X is the parameter which is going from 0 to BUR minus 1. BUR is number of buildings between transmitter and receiver. Now the next step is to obtain the building blockage probability. So building blockage probability, if suppose between transmitter and receiver, we have 3 buildings as shown in the previous figure. So for first building, the probability of line of sight will calculate. For second building, will calculate, and for third building, will calculate, and we'll multiply that line of sight probability to calculate building blockage probability. So this is nothing but the total probability of line of sight between transmitter and receiver. Then it will be used to calculate the estimated area coverage. So that will be based on the number of buildings between transmitter and receiver, and how much is probability of line of sight. So this is what is the algorithm given for the paper to estimate the area coverage. Then based on that, we had simulated these results for all 4 different environments: suburban, urban, dense urban, and high-rise urban. And these are the parameters for simulation. So the area is same which we had taken previously. The elevation angle is also same. We had taken altitude from varying altitude from 100 to 500 meters, then communication range from 100 meters to 1 kilometer. And distance between each building we had taken as 20 meters. Now, these are some of the results. So first set of result is the area coverage versus estimation angle for various altitude. So our main aim is to find out optimum value of elevation angle for particular altitude. So we can see that each and every area is following the pattern of the graph remains same, except that 100 altitude, it is showing the lesser elevation angle. And for 200 to 500, it is showing the higher elevation angle. And this is following for all the areas. So from that result, we had find out the optimum elevation angle. So optimum elevation angle is 60 to 80 degree for altitude 200 to 500 meters, and 35 to 65 degree for 100 meters. These are what is the results which we find out for our study. So based on that, we can find out the communication range, or how much area will be covered. Now, next part is for the result is the coverage range, how much range we can obtain for particular estimate of area coverage. So on that, for y-axis, we had taken area coverage estimation. On x-axis, it is range. And again, the four urban cities is being used. So we can see that for suburban, it is showing the different part, because it's a simple thing that as I'm going to increase the density, my range will be reduced. So as I'm going the density of the building, so my range is dropping out. For low altitude, it will be less range, and for higher altitude, it will be more range. As well as one more observation over here, that for suburban, the maximum altitude which we had taken is up to 300 meters. If I go on increasing the altitude above that, it is showing the similar pattern. So for the low altitude also, we are receiving good coverage for suburban area, because here the density of building is less. But for rest of the building, altitude is playing significant role on the coverage range. So from that, we can find out that first of all, the suburban we had taken maximum is 300 meters, and to achieve at least 50% of coverage, the distance between transmitter and receiver we can keep up to 500 meters. This is what is our observation based on the results. And effect of altitude, if I find out on communication range, as it is shown in the figure, that for suburban it is not a significant effect, but for a rest of the environment, altitude is playing significant role to identify or to find out the communication range. So based on that results, we can say that our work can be utilized for RF planning of disaster affected area without any prior knowledge of site specific information. So this is a generalized way to estimate or do the RF planning for disaster affected area. Now the key findings for our this is, first of all, we had developed an LOS based model. So we have developed a simplified equation which is based on elevation angle for low altitude. Second part, this study is based on statistical parameters. So this does not depend on 3D model of the site. And the next part is, it is very useful for disaster affected area where the city map is not available because the things are destroyed. So this study can be useful. And in the second part, we had done the coverage estimation. So we had, this is based on building blockage probability, and we had given a simple algorithm to estimate area coverage from the developed model. And we had studied the 3 parameters. So our coverage estimation, we had evaluated for 3 parameters: elevation angle, communication range, and UAV altitude, which is the important parameter for RF planning of UAV to ground communication. And we also defined the optimum values of elevation angle, which is 60 to 80 degree for 200 to 500 meter, and 35 to 65 degree for 35 to 55 degree for 100 meter altitude. As well as we had shown that our suburban is not much dependent on altitude, but rest of the parameters are much dependent on altitude while calculating communication range for coverage. And this study is not only useful for disaster affected area, this is also useful for planning of terrestrial network or for cellular network. There, this can be used as an aerial base station. So we can do the RF planning for those area also, and where the signal is not available. So these are some of the application, extended application of the study. Now here are the references, and then thank you very much.
Thank you very much, Ms. Ankita. I just have one question from the audience. If you design a system like what you have presented, what will be the weight and power requirements?
Actually, power requirement will depend on what type of communication you are using, because it is that range we are getting less for the density, for the urban and dense urban. So there definitely we need more power, but for the suburban power, we need a less power. So our actual next part is to estimate non-LOS and to do the path loss planning. So whenever we go for the path loss planning, that time exactly estimate we can give what transmitted power will be required. But right now I can say, for as we go on increasing the density, we need less power, and for suburban we can go with the less power of this.
I mean, I'm curious. I mean, how do you simulate these things? Because you don't have like hardware with you, right? So how do you simulate these things?
Sir, our planning is, the next part is that we'll develop a non-line of sight model. It may be based on shadowing effect or multipath part. So we'll design a complete model, path loss model. Then we'll do empirical analysis. Will take the similar kind of environment. There we'll just do the measurement setup, and then we develop the model based on that and compare our model with that. So our study will be at later stage, it will be a comparative study of empirical model with the designed model, developed model.
Okay, thank you very much. That's all from my side. Professor Adhikar, do you have a question?
No, I don't have any question. Thank you, Ms. Ankita, for your presentation.
Thank you, sir.
Now I will like to invite next presenter, Mr. Mohammad Noor. Are you
Excuse me, sir.
present?
Sir, he is not here. He already shared the video with us. So
Okay, all
we
right.
will play that.
Then after that, Mr. Abhishek Joshi.
Yes, sir.
Are you here? Okay, all right.
Yes.
So good. Welcome, Mr. Abhishek Joshi. So Mr. Abhishek is presenting his work on simulation of clustering protocol and mobility model for UAV network.
Yes.
So over to Mr. Abhishek, please.
Thank you, sir, and good morning, everyone. So the topic of my research is simulation of clustering protocol along with the mobility model for UAV network. The co-authors of this papers are Dr. Sarang Domudi and Professor K.R. Anupama. We are from EEE Department of BITS Pilani Goa campus. Now, unmanned aerial vehicles, they can be treated as mobile entities which have adaptive communication ability so that they can act as backbone for ground-based sensor network. Now, these UAVs along with the ground-based sensor network can form a three-dimensional network which can be termed as unmanned aerial network, abbreviated as UAN. And the UAN has found a multitude of application categories which have been listed below and have also been depicted into the picture. So the research interest for this paper has been considered to be the UAN used for disaster monitoring application. Now, for this research, we have considered a single disaster event in which the UAVs have been deployed in unstructured manner. And the aim of this research is the disaster event needs to be monitored and the sensed information data through the UAVs need to be conveyed to the nearest ground control station or the base station in real-time manner. So following assumptions have been made. The UAVs have been assumed to be equipped with GPS and IMU units. There is a flight processor associated with individual UAV. They have been also accompanied with a co-processor for networking ability. They have been accompanied with a communication unit which supports multiple power levels, and they have been also incorporated with battery. Now, the clustering protocol which has been described in this research has been elaborated in different phases. The first phase, the UAV first retrieves its ID, which has been fed by the base station node. Also, it retrieves its residual energy along with the position and timing parameters. And it feeds all this information into a custom message structure, which we have defined, labeled as neighbor discovery message. And it broadcasts this message 3 times at a random timing interval so that the reception probability has been increased. Now, after receiving the message, individual UAV generates a neighbor table, and upon generating the neighbor table, it calculates the connectivity value. And after calculating the connectivity value, the UAV node makes use of surface calculation part, which has been also elaborated into the table, to categorize itself into one among the 9 subphases. So the primary criteria for subphase assignment being the residual energy of the UAV, and the secondary criteria for subphase assignment being the connectivity value of UAV. Now, upon calculation of subphase, the UAV broadcasts another message which has been termed as UAV message, in which it includes the UAV ID, the residual energy of the UAV along with the connectivity value. After this, the cluster head election phase starts, in which the UAV receives the message, it extracts the message content, and what it does is preliminarily check the received energy parameter, because this is one of the primary election criteria for cluster head. It checks whether its own energy value is lesser than or greater than the received value. If it's greater than, it proceeds further into electing itself as a temporary cluster head. If it's not, it discards himself from cluster selection phase. Now, if both of them are equal, it compares the connectivity value with the simulate process. If both of them also turn out to be equal, it compares the UAV IDs, because they are turned out to be unique. They have been fed by the base station. Now, at the end of this phase, a temporary cluster head has been elected, and it starts collecting the entire network data on behalf of the network, and it forwards the data to the base station. Now, to implement this particular protocol, we have made use of an integrated simulation platform which makes use of network simulator along with the UAV simulator. The requirement for using an integrated platform being, if you use the network simulator alone, it works on probabilistic mobility models, and it does not have access to realistic UAV parameters which can be retrieved from the UAV simulator. And if we use UAV simulator alone, They have physical UAV simulation capabilities, but they lack networking abilities. So they have been integrated with the help of robot operating system, and it works on publisher-subscriber model to fetch and retrieve the data. Now the results have been discussed followingly. These are the simulation parameters. We have varied the number of UAVs, we have varied their speed. We have mentioned what type of communication channel we have used, what is the range for low power communication unit, what is the range for high power communication unit. In the initial phase, we have considered the UAVs to be hovering. So they have been assumed quasi-static, and they have been compared against the network lifetime parameter with the prominent clustering protocols, which are Leech and Heat. Leech being a completely probabilistic protocol, it performs with least amount of number of rounds the network can last. And Heat being a hybrid protocol, it takes into account the residual energy of the node, but it still takes into account the probabilistic aspect. So it still performs poorer than the proposed clustering protocol, which is the completely deterministic protocol because it relies upon the residual energy, also the connectivity metric of the UAV. Now, the UAV speed has been varied, the network has been considered to be mobile. And in this particular section, we are considering the mobility model, which is a realistic mobility model, which we have retrieved from the UAV simulator against the available mobility models which are available there within the network simulator. In network simulator, the mobility models have been broadly categorized into group mobility models and individual mobility models. But all these mobility models altogether work on probabilistic nature, because when a UAV reaches a particular point, it has to rely upon a probabilistic nature where to find out its next position along with the updated position, updated velocity. But in the case of realistic mobility, which we are retrieving from UAV simulator, it knows the exact position where the UAV has to go to with the refined speed. So when we are comparing the network lifetime with varying UAV speed, we can see the proposed mobility model outperforms first the group mobility model, which is RPGM, and further it outperforms the individual mobility models, which are Gauss-Markov mobility model and random point mobility model. So these are the conclusions of this research. Deterministic clustering protocol has been proposed in this research. It takes into account the connectivity value and the residual energy of the node. Further, it has been compared against the prominent clustering protocols, and it outperforms the prominent clustering protocols like Leech and Heat. Also, we have integrated a simulation platform which makes use of UAV simulator and network simulator, and a realistic mobility model has been taken into account, which has been compared against the prominent mobility models which are available within the network simulator, and the realistic mobility model which we have achieved from integrated simulator platform outperforms the existing probabilistic network simulator mobility model. And that is all from my side. Thank you, everyone. Any queries?
Yeah, thank you, Mr. Abhishek. You have presented on time, so I really appreciate it. Meanwhile, we have questions from the audience. I have a very short question. So when you think about the protocols, you always think of scenarios, right?
Yes, sir.
So what are the scenarios that you can think of?
Sir, currently what we are working upon, we are considering a disaster application. So let's say a case of currently for this research, we have been taken into account a wildfire situation. We are considering a temperature sensor and a smoke sensor has been equipped on individual UAV, and the sensing range of the individual sensor has been considered to be a spherical spherical sensing range, and that's how we are mapping the entire region, and the information is being conveyed to the base station. In the future work, we are doing the hardware deployment along with the actual camera unit deployed on the UAVs.
So, I mean, when you implement a protocol and when you just apply in terms of an application, suppose you develop a clustering protocol in an urban area, do you think that a human resource should be trained enough if we have any problems related to the cluster? I mean, like if we have one system, it is still you need a trained manpower, for instance, right? If you have a cluster of instruments, the thing will be more difficult, per se.
Yes, sir. So regarding that aspect, in the beginning of this research, we tried to think about this point, and that's how we are working on this situation to make the user involvement lesser and lesser as we progress in the research. So currently, when the preliminary test we concluded on the hardware testbed of 3 UAV, we have considered the simple line of sight without any obstacles. So the role of the human personnel is only to feed the approximate coordinates of the event, because at the end of the day, we do not know the exact coordinates. It will feed the approximate coordinates, and it will feed the UAV IDs, and we have stopped over there, the human involvement. Now the UAVs are autonomously flying in a straight line trajectory, and upon reaching the point where the boundary has been detected, they start dispersing themselves and start monitoring the boundary. So in this way, we have started working on reducing the human involvement, because as you mentioned earlier, that considering the UAV nature, the role of human should be less burden rather than he has to take control of everything.
I mean, great. I mean, we have a one short question from the audience, and then we finish this, this presentation. So one question is, what kind of radio communication or frequency range will you use for these protocols?
Sir, for within the cluster, when the UAVs are communicating with each other to save power, we have used low power communication UAVs, which is again working on 2.4 gigahertz, and which is 802.11 based communication system. And then when an individual UAV or a cluster head has to communicate to the base station, which is further from the UAV's range for low power, we have made use of high power communication unit, which is again working on 2.4 gigahertz system, and it is giving us a range of around 1850 minutes. So that only a cluster head communicates rather than everyone has to communicate at high power and consume more energy.
Okay, that's great. That's all from my side. So Professor Aditya, I think we have 3 video presentation that we just move because the speakers are not present, and we have 23 minutes left. So I think we just play them once by back to back, for instance.
Yeah, I think it will be good. Okay, yes, thank you, Mr. Abhishek, for your presentation. And now we will have all the videos from presenters.
Present in this conference. Our paper is titled 3D point cloud segmentation using a combination of ransack and clustering methods. There are 3 of us working together on this paper, each from 2 institutions, the Northeastern Space Application Center, or NESAC, from the Department of Space, and the Department of Computer Science of St. Anthony's College, Shillong. In this paper, we are working on point clouds, which are a form of data which represents real-world objects or scenes in 3D space. Now, each of these points has attributes such as an XYZ, which represents the coordinate in 3D space, and then the color attribute represented by these values, the RGB, and other additional attributes such as intensity, GPS time, normals, and so on. Now, analysis of such point clouds is necessary in order to understand real-world 3D scenes, which will lead to many computer vision applications as well as remote sensing. Now, the main challenges that we faced is that 3D point clouds, which are derived from drone images, which in our case, it is highly unstructured and has varied density. Now, furthermore, the problem increases when the given 3D scene are mixed together with natural scenes such as vegetation as well as man-made objects. Our approach, however, is to understand the 3D data, the available techniques in order to analyze this data, and suggest appropriate methods to precisely segment and classify the objects in the scene. In our case, our point cloud is derived from drone images using a process of photogrammetry whereby key feature points from each of those images are detected and form points in our point cloud. Now, segmentation of these point clouds is a process of labeling each measurement whereby each points belong to the same surface are given the same label. So in this point cloud, for example, we have a road as well as some buildings and then some trees. Now segmentation will allow us to label each and every point in this point cloud as to whether it is a road, it belongs to a road or a building or some trees. Now the segmentation process is quite challenging because of high redundancy and uneven sampling of dense as well as sparse point clouds, right? And then the lack of explicit structure of the point cloud data. Now, this is the point cloud that we have incorporated in our segmentation process. It consists of more than 720,000 points, and these are the attributes of at least one point in the point cloud. Now, as I said, our point cloud is derived from drone images. Therefore, it has very limited attributes as compared from point clouds derived from LiDAR. Additionally, the segmentation process also becomes quite challenging as our point cloud is again derived from images. Moving on to the methodology of our approach, we are using Ransack in order to basically filter our point cloud, right? And then the output, the remaining point clouds, which has not been detected by Ransack, we are using dbScan as well as Euclidean cluster extraction. In our segmentation process, we have used the Ransack algorithm in order to detect points which lie on the same plane in the point cloud. Those points which were not detected by Ransack, however, were fitted into the dbScan algorithm in order to detect other structures such as roofs, buildings, trees, cultivated areas, and a water stream. Now, even with the use of dbScan, there were some structures which were not detected, and for that we used the Euclidean cluster extraction, which detected 2 additional roof structures. So in summary, we are inputting our point cloud into our hybrid approach using planar segmentation using Ransack, and then dbScan, and finally Euclidean cluster extraction in order to obtain our final segmented point cloud, as you can see from the diagram. In our hybrid approach, we have incorporated the use of the Davies-Baldwin or the DB index in order to assess or determine the accuracy of the clusters that have been generated. Now, first of all, we process the entire point cloud using only dbScan, and then we calculate the DB index for each and every EPS value that we have set for the dbScan algorithm, and we chose the DB index with the optimal value, which generated a satisfiable number of clusters, and that turned out to be 1.83. Now, using our approach, that is the hybrid approach, using Ransack as well as dbScan and Euclidean cluster extraction, we have done the same thing, and we found the optimal value of the DB index is 1.76, which has generated a satisfiable number of clusters, which is 38. Comparing the normal approach, which is using only dbScan on the entire point cloud, with our hybrid approach, that is using Ransack as well as dbScan and Euclidean cluster extraction, we found that the DB index is much more optimal in our case as compared to that of using only dbScan. Furthermore, the execution time is also much lower in our case, as well as the number of clusters is also more in our hybrid approach. Now, looking at the challenges and limitations of our approach, we have no consideration of the semantic information of each and every point in our point cloud. And for that, we would require deep learning. Deep learning will obviously outperform our approach in most complex scenes. Now, one of the main reasons that deep learning was not explored or was not considered in our approach was because it is irrelevant to use existing point cloud datasets which do not showcase the topography of a certain region, which in our case is the terrains of the state of Meghalaya in India. Another reason is that most mainstream point cloud datasets are acquired from either LiDAR or RGBD. Now, in the future, these limitations can be overcome by moving towards a more deep learning approach, and additionally, constructing and labeling region-specific datasets in order to incorporate deep learning techniques such as semantic segmentation can be effective and will achieve greater. So in conclusion, our approach towards segmentation is simple yet effective, and the combination of different methods will yield different segments that are present in our point cloud. Now, although some methods such as dbScan produces small clusters, that are just blobs of vegetation, the overall segmentation process is still applicable and useful. Now, our hybrid approach allows fast running time and achieves good results, and the amount of computational power required is significantly lower than that of deep learning methods. So these are our references. Thank you.
So shall I play the next question, please?
Yes, please go ahead.
Yes.
Please go for next.
And sir, the author sent for the 15 minutes video, so I'm skipping the introduction part.
Yes, please. Please try to finish within 7 minutes.
Okay, sir.
Yeah.
So, okay. I think we'll give the very short presentation for the purpose of the regarding to the buffer zone that which is purposely for the to define the development, actually development, the development control Kuala Lumpur, which is our capital city. And then looking at the existing buffer zone, the distance of, we observed that the distance the nearest developments, which is the traditional settlements and the well-planned housing areas, the minimum is 0.1 kilometer to 0.5 kilometers. So I think this is something that we need to looking at because the emission that has been out from the industrial area possibly will be effect to the surrounded or the settlers that which is occupied the traditional settlements and also the other housing areas around surrounding the site. So the locations of the study area and the acreage is about 66.64 acres. So we just use a very small, there is actually the original census is actually carried 5 types of the gases. But for this study, we are only will highlight for 2 gases, which is carbon dioxide and also the hydrocarbon. So hydrocarbon is very synonym to the industry and also carbon dioxide. And of course, so we know that the effect of the CO2 and also hydrocarbon is possibly will give an impact to the surrounding human and also the land users. All right, and we are using the processing software of Sniffer 4D, that which is linked to this kind of the drone and the sensors. And then after that, we had done the post processing at the QGIS and also ArcGIS. So the fieldwork was carried out during the pandemic. And then we are lucky because we have a gap during that time, so, which is on the September. We have conducted this one, which is during that time, so our government is a bit loose because the cases is getting reduced, so that we have a chance to go to the fieldwork and then carry out the some certain result. But however, after that, so we have all of us is actually was in the restricted in terms of the movement. So the flight track at we had set up at the 100 meters height because the highest chamber is actually 80 meters. So that we need to the side is respectively which is below 1000 ppm, and then the average of the hydrocarbon is 0.078%, which is equivalent to the 780 ppm. So if you look the colors, these colors is actually is representing the range of the reading for the carbon dioxide itself. So the dark color, this one is actually is more the darker. It's actually showing the highest number, and then the considered as a bright color is actually is the lower range. Okay. So the result also shows that the study area is in a normal range of the outdoor of the carbon dioxide, but the concentration value maybe in future will reach the hazardous level if we are not able to control it. And the overall result shows also that the value of the carbon dioxide is between average 2.9 to the 90 ppm, and it is still below of the hazardous level of the CO2. And then the value of the hydrocarbon are 50 ppm and 700 ppm, shows the highest value compared to the carbon dioxide. But I think for the overall, it still is under control. Maybe we consider that area is a bit new, but still we need to look at this matter, because the locations of the industrial area itself is very close to the residential area and also the another settlement. And for conclusions, the development control on the buffer zone for the industrial area was tested through the risk of the environmental gases that emitted by the heavy industries. For in this case, we are testing the carbon dioxide and also the hydrocarbon which is emitted from the heavy industries. And then the finding shows that the existing buffer is too close to the nearest settlements, which is according to the guidelines, it must be the minimum is 0.5 kilometer. But most of the area we had observed is actually have also have the minimum 0.1 kilometer, that which is only 100 meters. So, and then we can just imagine the effect if the emissions can be able to distributed to the whole places, and then of course it will be affected to the nearest land users. The sniffer drone tested to the concentrations of the carbon dioxide and also the hydrocarbon are in normal range, except for the hydrocarbon, which is closely alerted. And then I think this is also agree that most of the hydrocarbon gases is very closely related to the what has been emitted by the factory, especially the heavy industrial. In this case, the government should find the precaution steps in order to ensure the compatibility of land users and at the same time on the human safety. And of course, we found that UAV, the usage of the UAV, especially with this sensor, is very reliable. And then it will become the alternative tools for the environmental pollutions monitoring and also.
Sorry, sir, I have to stop because one more video is there.
Yes, please go ahead.
Yes, sir.
It is okay, I think. You please.
Okay, sir.
Today I will be presenting to you the paper, The Role of Unmanned Aerial Vehicles in Smart City Planning and Management. A massive wave of urbanization has grasped both the developed and the developing nations in the last few decades. Various studies showcase the rising trend of rapid urbanization growth due to demographic shifts catalyzed by numerous global and local parameters. A United Nations study of 2014 states that by the year 2050, 70% of the world's population will be living in cities compared to 30% in rural zones. Similarly, it is predicted that by the year 2030, nearly 40 to 50% of India's population will be living in urban areas and contributing to 70% of the country's GDP. Therefore, to cater to the demands of increased urbanization, the concept of smart cities is being advocated as an apt solution. The most striking feature of the smart city concept is that it amalgamates the ICT solutions, that is, information and communication technologies, as an additional layer in the city dynamics for improving functionality and efficiency of urban services. Even so, there is widespread ambiguity pertaining to the challenges associated with the adaptation of smart solutions into the existing urban social form. Though there have been many tentative explanations regarding the basic framework of a smart city, there are no known validated definitions. The Government of India also launched the Smart City Mission in 2015 to facilitate 100 cities to become smarter and become the flag bearers of urban development for the entire country. Pan-city initiatives are essentially the ICT interventions strategically planned around the city with the help of sensors, big data, Internet of Things, UAVs, etc. The pan-city planning endeavors will support the area-based development strategies, namely retrofitting, redevelopment, and greenfield development. Information and communication technologies, or the ICTs, are an additional layer of infrastructure in the city, which function based on orchestration of intelligence, empowerment intelligence, and instrumentation intelligence. The underlying concept behind ICT Intelligence Platform is based on problem-solving, open platform cluster innovation, real-time data collection, and faster data analysis, processing, and response. The UAV, or drone as it is popularly known, is a device capable of flying or being flown on its own without a human pilot on board through prior computer programming or autonomous maneuvering. Even though it began with military applications, extensive ongoing research and development have made many advancements with respect to size, cost, typology, functionality, etc. So much so that now UAVs have large-scale commercial reach. According to use, the drone is classified on the basis of its intrinsic function. For example, drones for aerial photography, drones for traffic surveillance, drones for mapping of an urban area, drones for facial detection, etc. On the other hand, based on the aerial platform used, drones can be classified as single rotor helicopter type, multi-rotor type, fixed wing type, and fixed wing hybrid VTOL type. Within smart cities, drones can be used for urban agricultural needs, traffic management, environmental management, round-the-clock surveillance, disaster response, telecommunication, weather monitoring, mapping, resource estimation, etc. For example, in the Smart City Mission of India, all cities will have a central command center which will have the required IoT-enabled platform for data analysis, reaction, and storage.
Hello, sir. So I think this is a general thing, and the paper will be available after the publication, so we can refer, and we are limited with the time. We have to complete our session in 1 minute.
Yeah, it's okay. So thank you, Ms. Pratibha, and to all the participants as well as audience of this session. There are total 9 papers presented in this session out of 11 which are submitted earlier. Out of these, 6 papers are presented in person. In person means online, that these authors have presented live, and the remaining 3 papers were presented as a video recording presentation. So I think it is a very good session where we have got variety of works, variety of applications, as well as the technology improvement, including communication using UAV. So I hope all the audience must have been benefited with this new technology. So Professor Saurabh, you want to add something?
No, sir. I think I thank all of you, all the speakers and the audience, and the session will be live as well. I mean, you can see the video recording afterwards as well. And if you have any questions, you can reach out to the speakers. And thank you very much. That's all.
All right. Thank you. Thank you, the organizing team. Thanks to the organizing team, Ms. Pratibha and all others, Mr. Sunny, and all others who have contributed in organizing it nicely in online mode. Thank you.
Thank you, sir. I thank Professor Adigal sir and Saurabh Vijay sir for spending their valuable time and moderating the session and give their valuable expert reviews. I also thank all the participants for joining in the session. We will meet you in the upcoming session, sir. Hopefully. Thank you.
All right. Thank you.